Next, we're going to take a look at some basic properties of limits. So these are the so-called limit properties. And for what follows, it's going to be very important to note a condition on each of these statements. And that condition is that the limit as x approaches c of f of x and the limit as x approaches c of g of x must exist. So in other words, they have to actually give you a particular number. They cannot be infinity, right? They have to return 5 or 6 or 27 over pi. There has to be some numerical output. They have to converge, in other words. They cannot diverge. And all of these properties are only good for conditions under which these two basic limits exist. So as long as these two limits, so the function f and the function g, as long as both their limits exist as x approaches c, we get the following properties. If either of these limits don't exist, the properties aren't good. So the first one says that the limit as x approaches c of k times f of x is equal to k times the limit as x approaches c of f of x. So in other words, if you have a constant times the function, you can pull it outside of the limit for free. The second one says that the limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x. Like that. So in other words, the limit of the sum of two functions is the same as the sum of the limits. As long as each limit, so the limit of f and the limit of g, both converge to an actual number. And then finally the limit, well not finally, but the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x and then times the limit as x approaches c of g of x. And again, this only works if the two limits individually both are well behaved. And then our last one is the limit as x approaches c of f of x over g of x is equal to the ratio, the limit as x approaches c of f of x, and then divided by the limit as x approaches c of g of x. And there's a further condition as long as the limit as x approaches c of g of x is not equal to 0. So that fourth one has this additional condition, right? Because if the limit as x approaches c of g of x is equal to 0, we have a problem dividing by 0. And this limit might be well behaved. Like say, do a quick example down here. The limit as x approaches 0 of x divided by x. Well, the limit is just equal to 1. Because for every x value other than x is equal to 0, this ratio returns 1. In fact, that function looks like this. That's supposed to be a straight line. It just has height 1. So there's the x-axis, there's the y-axis. So it's just a constant function with a hole in it at the origin. So when we take the limit as x approaches 0, the y values are just approaching the output of 1. But notice this property number 4 doesn't hold, right? This is not equal to the limit as x approaches 0 of x divided by the limit of x as x approaches 0 of x. Because the limit as x approaches 0 of x is just 0. So this would predict 0 over 0, which is meaningless. It doesn't give you anything. So you can see why it's important that this bottom one cannot be 0. Another instance where these rules might break down, you can have a limit where the limit as x approaches c of f of x goes to infinity, and maybe the limit as x approaches c of g of x goes to minus infinity, but when you add them together, maybe you get 0. So the limit on the left would exist where the limits on the right don't exist. In that case, these properties wouldn't be valid because for each of these 4 properties to be valid, you need the limit of f to work, and you need the limit of g to work. And the final caveat on all of this is that all of these properties also work if you replace c with infinity or minus infinity. So these properties are also true if you look at limits as x goes to infinity or as x goes to minus infinity. To look at an example, say limit as x goes to 0 of 3x cubed plus 2x squared plus 7 over x cubed plus 4x plus 9. So basically these limit laws are oftentimes used as justification to break up things like this. So this is equal to the limit as x goes to 0 of 3x cubed plus 2x squared plus 7, and then over the limit as x goes to 0 of x cubed plus 4x plus 9. That's using limit law number 4, and you would justify this by saying, well, the limit of the denominator doesn't go to 0, which we still haven't shown yet, but it doesn't. It just goes to 9. And then you would further break it up as 3 times the limit of x cubed plus 2 times the limit of x squared plus 7 times the limit of 1. I'm just being quick and not writing x goes to 0 every single time. I'm just writing a limit, and then divided by the limit of x cubed plus 4 times the limit of x plus 9 times the limit of 1. Then you can say, well, the limit of x cubed as x goes to 0 is 0. So that wipes this out. That's just a big 0. The limit as x goes to 0 of x squared is 0. The limit, again, as x goes to 0 of x cubed is 0. The limit as x goes to 0 of x is 0. And then the limit as x goes to 0 of 1 is just 1. So these guys are all canceled out. So we get 0 plus 0 plus 7 over 0 plus 0 plus 9, 7 over 9. So the limit laws are oftentimes used to break apart a bunch of complicated functions into some easier ones. Next, we're going to turn our attention on an important theorem known as the squeeze theorem. So this is the squeeze theorem. So it says the following. So if, say, f of x is less than or equal to g of x is less than or equal to h of x, and if the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of h of x is equal to L, then the limit as x approaches c of g of x is equal to L. Right, so basically it says if you have, well, I'll show you the picture in a second. But basically if f of x is always, so there's h of x, g of x, and f of x. So h is always larger than g, and g is always larger than f. If it happens where there's a point where the limit as h of x, or the limit of as x approaches this point, x is equal to c of h of x, gives you the same thing as the limit of f of x, well then g of x also has to give you the same thing because it's sandwiched or squeezed between f and h. So let's see an example of this. So compute, or let's say prove, that the limit as x goes to 0 of x squared times the sine of 1 over x is equal to 0. So first of all, what does this look like? Well, sine of 1 over x might not be something you readily know how to visualize. Well, we know what sine of x looks like. Sine of x looks like that's supposed to be like nice and even. And it's just regular, and it goes like that on and on forever, and it just kind of repeats. It's just a sinusoid that repeats forever and ever. So, I'm just going to make up some numbers, whatever, 2 pi, well, I guess I'm not, 4 pi 6 pi, 8 pi, 10 pi, 12 pi, and so forth. So what would sine of 1 over x look like? So eventually we'll get to 1,000, 1 million, 1 billion, and the limit as x goes to infinity of sine of x does not exist. So they say it diverges by oscillation, right? And the whole idea is that the outputs never settle down to a particular y value, right? They're always going back and forth, so they never actually settle down on a particular one. Now what we're doing when we look at sine of 1 over x is we're taking x is equal to 1, and we're taking all of this, so everything to the right of x is equal to 1, and we're moving it onto the interval from 0 to 1. So we're kind of reversing it and squishing it. And the further out you are in x, the more you squish you get towards the origin. And the reason is because if you look at sine of when x is equal to 0.1, that will give you sine of 10. Right? So x equals 0.1, this will be sine of 10. When x is equal to 0.01, this is sine of 100. So we go from 10 to 100 in the x values for the sine, for the argument of sine. When x is equal to 0.001, we get sine of 1,000. So as x approaches 0, the arguments of sine get larger and larger and larger, and they do so at a tremendous rate. So this whole portion of the wave gets taken, turned around, and then crammed between 0 and 1. So what does that look like? So sine 1 over x, let's start here. In fact, maybe it doesn't oscillate much at all. It's probably only a fraction of an oscillation outside of 1. But then what's interesting is when we get close to 0, these oscillations quickly get closer and closer and closer together. Remember, they're oscillating up and down between +1 and -1. They just go up and down, closer and closer and closer and closer and closer and closer and closer together, and there's an infinite number of them. So it never settles off at any particular y value. It's just going up and up and up and down and up and down, up and down. So this guy itself, the limit as x goes to 0, does not exist, for the same reason that the limit as x goes to infinity of sine of x didn't exist, because it just keeps oscillating, without ever settling down at any particular y value. Now what happens when we multiply this function by x squared? So that's basically like taking the function, supposed to be a nice y is equal to x squared, and using this as the amplitude for a given value of x. So instead of seeing these go up and down between 0 and 1, what we're seeing, so let's do, there's plus x squared, it's a nice one, and then we have minus, so y is equal to minus x squared. So these, we get oscillations that start to get tighter and tighter and tighter. But now their amplitudes are squeezed between minus x squared and plus x squared, and they keep going back and forth faster and faster and faster and faster and faster. The amplitudes are squeezed in there. And the same thing on the other side. They start going back and forth faster and faster and faster and faster. But the amplitudes are squeezed in there. So how do we prove this using the squeeze theorem? Okay, well, the upper function is x squared, and the lower function is minus x squared. So it's very simple. Sine of 1 over x is always less than or equal to 1 and greater than or equal to minus 1. Right. So that's just a fact that the output of sine of x for any x value. What happened? Right, so the output of sine of x for any x value always returns a number between -1 and +1. So it doesn't matter if you get something fancy schmancy on the inside of the sine. It could be sine of something really complicated. The output will always be greater than or equal to -1 and less than or equal to +1. So then when we multiply it by x squared, the same thing has to be true. X squared times the sine of 1 over x has to be greater than or equal to -x squared and less than or equal to +x squared. So this gives us our f of x, our g of x, and our h of x. So all we have to do is say, well, x squared sine of 1 over x is greater than or equal to -x squared, less than or equal to +x squared, and then we just have to say, well, the limit as x goes to 0 of x squared is equal to 0, and the limit as x goes to 0 of -x squared is equal to 0. So therefore, by the squeeze theorem, the limit as x goes to 0 of x squared times this, sine of 1 over x, also has to be 0 by the squeeze theorem. And that proves that picture.